Hi everyone. This will be a crude but hopefully helpful introduction to functional maps for those who want a quick minute-long overview. This is a miniature version of a seminar that I did back in 2023. If you've clicked into this video, I am sure you know what you're looking for. We are concerned with the topic of shape matching. Specifically, for two given triangle mesh surfaces, we want to establish a dense point-to-point correspondence. So this is a central task in computer graphics and computer vision with applications, for example, in texture transfer, shape interpolation, or in areas like life and medical sciences. So this representation is itself a small matrix, but it can encode high-quality mapping information between the shapes, and its computation and inference is very efficient. The introduction was back in 2012. In 2023, it's been awarded with Test of Time. Throughout the decade, functional maps has been the central recipe for a ton of shape matching methods. These are listed here to establish its importance to the field. Let's start with a simple setup. When we talk about point-to-point correspondences between a pair of rigid shapes, we know that the rigid prior boils down to only 6 degrees of freedom, and all correspondence information can be represented by a simple rigid transformation. For example, a 4x4 matrix. So this is a really nice and concise representation because even if we have tens of thousands of vertices or points in our shapes, we only need 16 entries to accurately describe that. This is an overstatement as only 6 degrees of freedom is needed, but anyway, this conversion between the 4x4 matrix and the dense correspondences is nothing but the simplest form of linear algebra and finding the nearest neighbors after this rigid alignment. So, this relationship has enabled very simple and very effective algorithms like the famous iterative closest point, for example. So that was really nice, but for non-rigid tasks, people actually want to find something similar, in the sense that we want something as compact as a small matrix to limit our solution space, but we also want it to be accurate. Without the rigid assumption, if we just try to work on point-to-point directly, this could really easily get out of hand as it's an NP-hard problem. So what's the magic here? It really comes from the spectral domain. Usually, as we know, spatially complicated problems could become simpler when we are performed in the spectral domain. So that was the concept of functional map. We'll go through some intuitions, and eventually I want you to look at it just like a regular linear rigid alignment. To perform anything in a spectral domain, we first need a set of bases. There's no better analogy here than the Fourier basis analysis with 2D Fourier bases. This can be used, for example, image compression. We can do from an image function to its coefficients, or vice versa. For us, we really use something similar. Tangibly, we use a set of bases that comes from the vibration modes from low to high frequencies. This can be observed from a famous Chladni-Sand experiment, and this is exactly what we use. Mathematically, they are the eigenfunctions of the Laplace-Beltrami operator, and they can be defined for any general surface. With a set of bases, now we can do stuff with it. For example, we can compress a point map between two shapes using two of the bases that result in something of the size of k by k, and we result in the spectral coefficients for the point map. So this is one of the definition of a functional map. Intuitively, think of it as making a sandwich with the bases and a point map. And you can recover a point map by use the two bases in the reverse order, or intuitively flipping everything inside out. And you can expect the recovered point map is a soft fuzzy matrix instead of a hard assigned point map. You can think of it very roughly as a probability distribution, if you will. Then you can perform some kind of argmax operation to get back a clean and crisp point map. As you can imagine, as we use more and more bases for this representation, the crispness and accuracy for this representation can get better and better. From here, we should emphasize a second perspective of this small matrix. So note that a point map can transfer functions between two shapes. Recall our function map definition. It serves as a mapping or transfer of any function coefficients. So this is doing exactly what a point map does, only that this is done in the spectral domain. Now, let's come into a third perspective. The introduction will come from just simply rearranging this existing linear relationship by just a little bit. And now we are able to notice that this looks like something similar. It looks like the rigid alignments. It says a function map aligns together the two bases from the two shapes. So instead of the x, y, z coordinates, it aligns the bases. So you can really look at it as some kind of coordinates of a spectral embedding. Actually, you can literally look at it as the coordinates, except that this is k-dimensional. But we can still visualizing it using maybe the first 3 dimension, and this is what the spectral embeddings look like. Here, I would like to show you an animation of this perspective once more to illustrate. First, we decompose a shape and obtain a set of scalar basis functions. These are defined for every surface point. What I am showing now is every vertex point in its spatial location, and I'm interpolating them into the first 3 spectral bases. We could pick a different 3 and another different 3. For between two shapes, these bases can be linearly aligned with exactly our k by k function map matrix. Once they are aligned, we're able to retrieve point-to-point correspondences just by finding nearest neighbors in this spectral space. So very naturally, we could do iterative closest point for functional maps just like a rigid case. Even better, you can do fancier optimizations by iteratively converting back and forth between the function map and the point correspondences while increase the spectral basis number. This gives us a very simple yet very effective result. This method is called zoom out figuratively. In summary, a function map is the alternative to the rigid transformation, but for general non-rigid shapes. So we have gone over these relatively fast. The central takeaway is that everything becomes compact and completely linear. Now, an important question arises here. What's the magic? Why is it even accurate? There is an especially unintuitive aspect when we compare it with the image encoding example. On the left-hand side, I'm showing you an image example encoded with 150 basis coefficients. On the right-hand side, we have a 30 by 30 function map and a texture transfer. Notice the function map has mostly diagonal entries, so probably there's much less than 150 that is deviating from the 0 values. Yet, we're looking at the texture transfer nearly indistinguishable from the ground truth. So there has to be something that seems to have glitched with our intuition that we have built up from here. So the key difference here, I think, is about the prior assumptions that we actually have for the shape correspondence problem, but the image example is not giving. I can show you one example of what happens if we actually make use of a very strong prior to recover a blurrier image. So this is just one of the random example of recovering pixelated images to text that I have found from the internet. So with this in mind, does this actually make more sense? Now let's understand more about our specific prior. It really comes from the properties of the bases. They are invariant under isometric deformations. Think of isometric property about we have the same human shape, but we can be in different poses without stretching our surfaces. And the isometry is now our strong prior assumption in place of the rigid assumption. So basis functions can actually exhibit highly similar patterns. which allow them to be very easily matched together on the diagonal entries. This is very important for a function map approach, and a good function map will have a clean and near diagonal structure. However, when this kind of assumption does not hold, say maybe we have a non-isometric shape now, you can think of it as there is actually stretches along the surface. In this case, the function map, well, they will still work, sort of, although the performance of these bases will start to degrade. Nonetheless, these basis functions are one of the most versatile and most robust choices out there to use. And from the introduction of function map from a decade ago, numerous applications have been built on top of these Laplace-Beltrami bases. To name a few, we have the axiomatic zoom out that we have already introduced. There's another one called smooth shells. We also have supervised deep learning methods with function maps. There's also unsupervised deep learning methods with function maps. With that, I think we can wrap this up really quickly. If you are actually interested to explore more recent works, you could check out our hybrid function map work. If you are looking for a more formal and systematic introduction on functional maps, these resources from the original authors are highly recommended. With that, thank you for watching and see you next time.